My name is Daniel Campello, and I'm here to present non-blocking writes to files. This work was developed at Florida International University at the School of Computing and Information Sciences. It was done in collaboration with Hector Lopez, Useche, Ricardo Koller, and Raju Rangaswami. Applications today have different alternatives to persist their data. If they have strong requirements on the persistence of its data, they will use synchronous writes. So in this scenario, process will write, the write will be committed to the page cache, but immediately will have to be flushed to the storage backend. Until the write doesn't reach the storage backend, the application won't make further progress, but it can have the guarantee that the data was persisted. On the other hand, if the application does not require such a strong guarantee, it can use asynchronous writes. So in this scenario, the process will only commit the write to the in-memory page in the page cache and will continue executing. If at a later moment it requires for its data to be persistent, it can issue a fsync system call to force the data to be flushed to the storage. Furthermore, the operating system will make sure that there is no stale data in memory for a long time. And a kernel thread will force those data to be flushed. When an application is using asynchronous write, it's expecting very low latencies to write their data. But this is not always true. In some cases, memory access granularity is smaller than a disk. And this makes that if a write is a partial overwrite to a page, and that page is not present yet in the cache, the write will block until that page is fetched. The following diagram illustrates this. A process will issue a asynchronous write system call. The OS will handle this, and it will realize that there is a miss in the page cache. At that moment, the OS will issue a fetch and will put the process to sleep. Later in time, when the high latency I/O finishes, the page will be present in the page cache, and the OS will apply the changes that were requested by the application. Later on, the process will have the control to keep executing. But why wait for data that the application doesn't really need? To further analyze this problem, we took several traces in production systems at FIU, and we also analyzed two available traces from previous work that were collected in Android systems while using two different apps. We analyzed those traces, and we examined all the write system calls that were issued. And the following graph depicts the breakdown of the sizes of those writes. In blue, we have all writes that are smaller than a page and that will partially overwrite just one page. In red, we have writes of size of a page or bigger, but that are not aligned to page boundaries. Those will have a partial overwrite to the first page and or to the last page that they touch. For completeness, we show in yellow the amount of writes that will completely overwrite existing pages. Those won't require a fetch. And in green, we have writes to new pages that will not require a fetch either. On average, 63 of all these writes involve partial page overwrites. But you can think that not all of these will require fetches. It will depend on how many of those pages are already present in the page cache. So the size of the page cache will be a big factor on top of the workload that we're dealing with. To further analyze this, we run an LRU simulation, and we show here a curve showing how many of those writes will be to pages that are not present in the cache, and that would require a fetch. The two lines that are in the graph represents the two first workloads, which are file server workloads. And we can see that even for big sizes of the cache, 100 gigabytes, we have between 10 and 20% of all writes would require a blocking fetch. For the remaining workloads, we see different patterns, but we can see that for bigger sizes, we have between 7 and 45% of all writes will require a blocking fetch. So how we deal with this problem? We have two approaches. The first of them is the non-blocking writes asynchronous fetch. And here again, the process will issue a write system call. The OS will miss on the access to the page. It will issue the page fetch, but instead of putting the process to sleep, we'll take the contents of the write system call and buffer it somewhere else in memory, what we call a patch. At that moment, it will return control to the process and let him execute. At a later time, the I/O will complete, and before making the page accessible to the system, the contents of the patches will be applied to those pages. So this approach has two benefits. The first of them is that the application execution time is reduced. And this is due to the fact that the process will be able to further execute while the I/O is done in parallel. The second benefit is that now the backing store bandwidth will be increased. And this is because since the process can keep going, it will be able to issue even more fetches, which can be handled in parallel and in a better way, depending on how the scheduler will deal with them. But we can see that here we're still issuing a fetch. So why issue a page fetch for data that the application might not need? So then we came up with a second approach, which is the non-blocking write lazy fetch. And the idea here is that we only issue the page fetch if it's completely necessary. So again, there will be a write, and that will mean a miss on the page cache. At that moment, we will buffer the contents of the write in a patch and let the application continue. At a later time, the application might issue another operation that on the same page, let's say a read. Here, if the read is requesting some contents that are not already buffering patches, we do have an optimization called read from patches, which allows the system to service reads from the contents of the patch, avoiding the fetch. But in the case that this is not possible, there will be another miss, and at that moment, the page fetch will have to be issued. The process will have to sleep until that is completed, because there is no other way to service that read. And once that happens, the contents of the patch will be applied to get the most up-to-date data and return to the process. So this approach has benefits and drawbacks. The benefit is that the allocation of the page and the fetch is only done if necessary. There are some scenarios where it can be completely avoided. If an application does enough writes to a page to completely override the whole page, the fetch becomes unnecessary because the previous data is not required. As a drawback, we have that resource utilization becomes unpredictable and can be bursty. Until now, I have presented two different ways on of when to issue the page fetch, which we say that are page fetch policies. The synchronous and lazy page fetch policies. But we also have the question on how to deal with those fetches. And we present two different mechanisms, foreground and background. These mechanisms are motivated due to the fact that even though we can do issue data fetches in the background, there may be some other metadata misses that will generate extra blocking fetches. So in the foreground case, the idea is that the process requesting the write system call will issue the necessary fetches. And if there are metadata fetches, we'll have to wait until those fetches complete before returning control to the process and issuing the data fetch in the background. So this has the advantage that the system does not need extra extra entities to carry up the fetch, but has the drawback of extra blocking due to the metadata. To overcome with that, we have the background mode, and here we have an extra entity, the kernel thread, and the idea is that the process that is requesting the write will let the kernel thread to carry out the work of fetching the page. If there are metadata misses, the kernel thread will block instead of the process. So we found that this problem is present in several operating systems, not only in Linux, but we implemented our proof of concept solution in Linux by modifying the generic virtual file system. And we evaluated this using the Filebench micro benchmark to get insights of how the system will behave under specific patterns. We also use the SpecSFS benchmark. We simulate the workload of file server. And to get an idea of how a real world workload will behave, we use the system call trace replace of MobiBench. So here we have first the results for two personalities of Filebench, one that does only random writes and one that does a mixture of random writes and random reads. In blue, we have the performance of the system under the original solution. We can see that at 4K, there is a spike on number of operations per second. And this is due to the fact that these writes will completely overwrite the contents of a page. And in that case, the fetch is completely avoided by the original system. For any lower size, there will be a partial page overwrite, and the system will have to block fetching those pages. In red, we have the results for the non-blocking write, asynchronous, and foreground mode. They seem to overlap, but in a closer look, we can see that we have 50 to 60% improvement on random writes. This limited improvement comes to the fact of the metadata misses on those pages, or those randomly accessed pages. To further improve on this, we have the results for non-blocking write synchronous background mode. Here we can see that as we increase the size of operation, there is a reduced amount of operations per second. Our system has a limited amount, we limited the amount of memory that can be used for patches. So as the operation sizes increase, the same amount of memory will hold less amount of patches. Once we reach that limit, we basically roll back to the original solution. We can see that the asynchronous background mode yields 30x performance improvement for random writes and 20x performance improvement for random read writes for the lowest amount of the lowest size of operation. And for the biggest size of operation before reaching the page size, we get 6x for random writes and 3x for random read writes. To further improve, non-blocking write lazy avoids to issuing the fetches, and we get up to a 45x performance improvement. Another personality is random reads. Here we the micro benchmark won't issue any writes. In blue, we see the original system, and we see that even for 4K sizes, we have a very low amount of operations per second. This is to be expected since the page is missing and there is no other way to service the read without fetching the page. The different personalities of non-blocking writes will do similar, and we get to the conclusion that non-blocking write does not affect performance under the presence of only reads. In the paper, we analyzed other personalities, and we present many more results using Filebench. For the SpecSFS evaluation, we have non-blocking write running on the server side of this benchmark. This benchmark will be running on a client side issuing NFS operations to a server. And it will issue a mixture of operations depending on a specific mixture of operations, sorry. So 10% of all operations will be writes, and we see in the normalized graph that the different modes of non-blocking writes can improve around a 70% write latency. For reads, we see that reads are not affected by non-blocking writes, by the exception of the case of non-blocking write latency, where we see a slightly affected latency. And this is due to a delayed fetching of some pages. In the original system, some writes that occurred before will have brought those pages into memory by the time of the read. With latency, the read will experience some extra latency by bringing those pages into memory. Others, which represent the 72% of all operations, are metadata operations which not contribute significant to the overall latency. So the overall latency, we can see that the different modes of non-blocking writes improve on them, and they improve in direct relationship to the write and read latency. Finally, for the MobiBench system called trace replay, we see here we present results for two different apps, the Facebook and Twitter apps, and we use HDDs and SSDs at the back end. The blue line represents the latency of all I operations done on the while replaying the traces on the original system. And then on red, yellow, and green, we have the three different systems of non-blocking write. We can see that all of them improve between 20 and 40% the latency of operations when replaying these traces. So there has been a lot of work in optimizing write performance, but here I want to mention two of them that seems to be very close to what we're doing. There is the unblock flag for open system call available in Linux system. This flag allows a process to execute writes and reads without blocking. But in the case of the page being missing in the cache, the operation will fail, saying to try again once the page is present. It will also require application modification to use this flag. You could also think about the Asynchronous I/O library. This library is implemented in user space and uses multiple threads to perform I/O operations. The manual for this library says explicitly that it can be expensive and scales poorly. It will also require application modification to make use of this library. In contrast, non-blocking writes do not require such application modifications. This is completely implemented in the OS transparently. In conclusions, operating system block processes on asynchronous write in many cases. With non-blocking writes, we demonstrate that such blocking is unnecessary and can be detrimental to performance. We propose a general solution that can be applied to any modern operating system and does not require application modification. Our evaluation demonstrated how non-blocking writes effectively reduce write latency across a wide range of workloads. This work was supported by NSF, Intel, and NetApp. And in the link on the slide, you can find the traces that we use. We made them publicly available. With this, I conclude my talk. I'm happy to take any questions. Thank you.
Hi, this is Juan from NetApp. I wanted to ask you, did you measure how much memory you needed for the batches? Or?
We basically put a hard limit on those. On the results that we show, we only have 64 megabytes reserved for that memory. If you would increase that region for patches, you could even get higher number of operations per second, since you can even delay more fetches.
Hi, Justin Mazzolo-Posca from Editor. So if you write to the same page in small increments multiple times, do you generate multiple patches or do you coalesce them?
We have optimization, when possible, we try to merge those patches to consume less memory.
Peter Desnoyers, Northeastern. Actually, to follow that up, I mean, this has been fascinating, but it certainly seems to fly in the face of everyone's intuition that most Unix file activity would be create once rather than overwrite. Now, I'm wondering if you, in fact, are writing a file in sub-page size chunks, would the second and third chunk going to the first page count as overwrites under your the way you're measuring things, in which case that would fit my intuition, or do I need to read the paper a few more times?
Just give me a second. When we were analyzing the traces, we collected several information on when the access occurred. The trace will contain which inode which file is being touched, the size of the file at that moment, the offset of the write, and the size of the write. So if the block is existent and is not present in the cache, and the write is smaller than that, the size of the write is smaller than the size of the block, it will have to be fetched. And that's how we basically we built this breakdown. On green, we have all those writes that will be to a new blocks, and that won't necessarily require the fetch.
Thank you.
You're welcome.
Hi, Nadavamit Technion. Did you simulate the behavior of the prefetch mechanisms that prefetch into the page cache more pages once you access it?
Sorry, can you repeat that?
Did you simulate, when you simulated your traces, how the page cache is being, how files are being prefetched into the page cache once one page is accessed, one block is accessed?
That's a good question. I'm not quite sure if we simulate that on the read patterns, but by investigating how Linux handles writes, the fetches due to write misses will not generate prefetching.
Thank you.
We've got time for maybe one quick question left. Final question.
Yeah, just Michael Condit, NetApp. Hi, Daniel. If an application needs durable writes in the face of possible crashes, then wouldn't you have to either be using battery-backed DRAM or storing these writes in flash, say?
Remember that the scope of this work is asynchronous writes. And when applications use asynchronous write, they're willing to sacrifice the persistence of those writes. If the application requires that persistence, we'll issue an fsync. At that moment, before returning fsync, we'll make sure of fetching the pages, applying patches, writing those pages back to the backend storage before returning the fsync.
Thanks, that's what I was thinking of, fsync.
All right. You can ask questions, I think, offline. We need to let the next speaker start. So
thank you
very much.